Great. Hi, good morning, everybody. So I'm going to talk about the International Deep Planet Survey. This work has been started 13 years ago, I'd say. Not okay? Yeah? So it has started 13 years ago at CAEC. And I will talk about several things. I will first try to answer the question, why are we doing direct imaging? Then I will present the IDPS survey. I will talk a bit about the automatic pipeline and databases that, and that's okay? Yeah, and databases that we developed, and then I will talk about new detections and the planet frequency at large separations. But first, why direct imaging? If you look at this graph, you have here, so here's the planet mass against the semi-major axis of all the exoplanets that are known today. And you can have here the technique that was used to detect the planets. And you can see, we could say a lot of things about this diagram. We just focus on the number of detection as a function of the separation. You can see that closer than 5 AU, we have a lot of detections using radial velocity and transit. But further, we have only a couple of detections, as Beth has just said, and we can only use the direct imaging to detect planet over there. And if you go to statistics, it means that closer than 5 AU for giant planets, we have a lot of information on the planet frequency as a function of the planetary mass and the semi-major axis and the stellar properties. But further than 5 AU, we don't have a good idea about this planet frequency. And that's why 13 years ago, we started, members of our team started the International Deep Planet Survey. Actually, it was called the CAEC survey at this time. And so we used a lot of instruments. First, NERC2 at CAEC. We have data taken before 2004. At this time, all these techniques as ADI, Loki, whatever, didn't exist, well, wasn't used actually, so the images have only a shallow contrast, so we can look for very massive planets in these images. After 2004, we have used ADI, so we could get very deep contrast and detect fainter planets. We also used NIRI at Gemini North, with good data and good contrast. We used Niki at Gemini South with using ADI and also SSDI, so spectral differential imaging. There, the contrast was very good too, but the instrument has been decommissioned this semester. We used also a couple of data taken at NACO, at VLT with NACO, and which is quite important, I looked into public data for second epochs to confirm that our candidates were planets or were just background stars. And you can see that it corresponds to about 100 hours of integration time, which is quite important. I will come back on this later. So if you add all these integration times that we have in the IDPS, it's about 1,000 hours of telescope time and tens of thousands of raw images. And a couple of years from now, it was 2010, Christian Marwa hired me. This is Victoria, actually, the observatory here. And he asked me to reduce all the data of this survey. So I came, it was very nice. It wasn't very sunny, so I could work a lot in my office. Yeah, he told me it was sunny, but it wasn't during winter. So I worked on my Blackboard, and I asked him to come when I got the solution for the IDPS pipeline. I think he was quite happy about that. And actually, it works in several steps. I won't go through all the details. There are very basic data reduction procedures, and then we register images, we apply the speckle suppression techniques, then we flag the planet candidates. This is the only step that is not fully automatic yet. Then we work out the astrometry and photometry of the candidates, accounting for all these biases that you have just mentioned. And we fill out the databases and apply a Monte Carlo analysis to derive the science interesting things from this survey. Sorry. So I won't go through all the 5 first steps. I will just focus on the 6th one and the 7th one. Why do we do databases? We have to gather all the information and then to interact with all these thousands of images and hundreds of stars that we observed. I developed a website that interact with all these databases. So here is an example with a peculiar star and all the stellar properties, how many times we observe the star, with which telescope, and so on and so on. And this is very useful to prepare to the new observation nights. Another database that is quite useful is all the contrast curve that we have. For each star that we observe, we have a contrast curve, and this is examples of that gives a contrast in magnitude against the angular separations. The shadow curve corresponds to data taken before all these ADI low-key techniques were used. The deep contrast curve is very typical for data taken with NERC2 at Keck using ADI, or data taken at Gemini South with Nikki using ADI or SSDI. And the median is the median. So we have about 500 contrast curve. Another database which is quite interesting for sure is the one with all the planet candidates and also the multiple stellar systems. Here are binaries, here is a 3 stellar system, and here are candidates to be planets. And actually there are more candidates, there are a lot of candidates. So again, we had to organize all this data, and the website, I can use it to go and to search for the planet candidates that I want with all the information that I need to know if I want to follow the candidate or not. We have access to the images and so on and so on. And when I did that, it was 1 year ago, the idea was to use it for the IDPS, but also after to gather information on all the surveys about direct imaging. I told you that I saved about 100 hours of telescope time looking into public data. If I had such a website, I would have been very happy. I would have saved time of my working in office too. So the idea was to develop such a website, and actually, at the same time, in the context of the Sphere consortium, they were developing what is called the DIVA website for direct imaging virtual archive. And the idea is exactly the same, except that it's an expert in website that is doing this website. Because I'm not an expert, so I did that in PHP during the night, but this is a real guy doing that. So I encourage people who have survey to share their public data, sending an email to Gaël Chauvin. So we could have one website for everybody, and it will be very useful. So in this website, for example, we could have such graphs, which gives the astrometry of a candidate that has been detected several times at several epochs. And here you have the positions measured in the images in red and blue, and in green you have the expected position if this object would have been a background star. You can see that the two doesn't fit, so it means that this object is a planet, actually. There is no surprise, it's HR8799c. But we come now to what new planet do we have? Actually, this system that Bates already showed, so here is planet B, C, D, and E. This system has been discovered as part of the IDPS. So it was very exciting, and when it was done just before I arrived in Victoria. So I arrived, reduced all the other data, and I was quite happy because I found 2 new systems, HIP114189 and this HD star. But actually, talking with Christian, he was just like, yeah, good job, but we already know that. but it was cool because I knew that my pipeline was working, actually. So we had another very interesting candidate, that one. So here you have one bright source, here another one, and here you can see a faint source. And then I will go to, so it was in 2006. And then 6 years later, a few months ago, we had an observation at Keck, and here you can see the bright source, here the other one, and here the faint one. I will go, and you can see that the background stars just move. The other not. The other doesn't move. It means it's a planet, so I was quite happy doing the Keck observations. Here is Christian checking his email, I guess. So we asked for new time at Gemini. We observe the star, we get the contrast, but we didn't find anything. And so I worked a lot on this Keck data during several days. It was quite exciting, a new planet, and actually it was a really, really tricky Keck PSF structure. Yeah, I could hear it here. No, it's the same for me. But just a message, be careful when you are doing direct imaging. You can have very tricky false detection. Anyway, we still have a couple of candidates. Here is one, here another one. And I will just sum up all the detections made with the IDPS. We have 15 new binaries, 2 new triple stellar systems. We confirmed 300 background sources, which will be useful for other surveys because they will come here and know they don't have to reobserve the star. We got 4 Jupiter-like planets, and we still have about 50 planet candidates within 200 AU, but actually, I would say that 8 to 10 are very interesting. The other one are really expected to be background sources. So what about the planet frequency? Now we have all these observations, all the contrast curves, the 4 detections. We do Monte Carlo statistics, and the sample for the IDPS is composed of 220 stars. You can see it in dashed line. So there are young stars close to the sun with mostly A and F stars in the sample. And I merged the Gemini Deep Planet survey and Dizzynas survey to reach 350 stars. And they are also young, close to the sun. But there are more GKM stars in these 2 surveys. So we got a pretty flat distribution in spectral type of the host star. So I do Monte Carlo. I won't go through the detail, but you just draw fake planets. You put them into your images. You look if you should have been detected them or not. Then you get the probability of detection around each star. And doing bias probability, you can get the planet frequency. And you get this kind of distribution of the planet frequency. This is for the IDPS sample, so you find that you have about 3 to 4% of stars that harbor a 1 to 14 Jupiter mass planet between 5 and 200 AU with this 1 sigma error bar. And when you increase the number of stars in your sample, here is the IDPS plus GDPS, you can you have a smaller error bar, and then you go on and you go on and you merge more and more surveys to reduce the error bars. So it's obvious, the more stars we have, the best it is for the error bar, but it was just a reminder. So just use all the stars from these 3 surveys. We got that 2% of stars harbor 1 to 14 Jupiter mass planet between 5 and 200 AU. The question is, and it was, I think, a question right before, does it depend on the stellar type? So I split the sample into 2 parts, BAF stars, which are mainly A and F stars, and GKM stars. And I look at the distribution that I found around these 2 stars. Around massive stars, we have about 6% of stars that would harbor such a planet. And around JKM stars, we have less than 3% that harbor such a planet. So we could say, okay, there are differences, but look at the error bars. For the moment, we cannot conclude. It's just maybe. So to answer that, we should merge these surveys with Niki surveys, the NACO-LP survey, SEED survey, and all the others. So we will reduce the error bars, and maybe we will conclude on this question. So I'm going to just conclude now. The IDPS has been running for 13 years. We detected 17 new multiple stars. We still have about 50 candidates, I would say 10 real candidates for planetary companion. We confirmed 4 exoplanets. The pipeline that we developed has been used as a base. I mean, the idea of this pipeline was used to develop the GPI pipeline. About the science conclusion, we found that about 2% of stars harbor a 1 to 14 Jupiter mass between 5 and 200 AU, and it may depend on the spectral type of the star, which would be quite important for people working on the model of formation of planets. The future is for the next semester, if the weather is good, we will finish the IDPS doing the last follow-ups of the candidates. We will release the IDPS website. Yeah, I spent a lot of nights, so I just want to be a bit public now. But I strongly encourage you to participate into this DIVA project to gather all the information of all the surveys. And for sure, the next step is what we will get with these very funny instruments, and maybe we'll have a very nice surprise. Thank you.
Thank you, Raphael. Questions? Here, Mike. Get the mic.
Thank you. Michael Liu, University of Hawaii. I just wanted to comment. I think it's great that you guys, actually a lot of people are doing this very advanced statistical analysis, but I just wanted to comment that I find it a little bit dissatisfying in the sense that when you quote these sort of frequency numbers, they're actually removed from the data in the sense that the Bayesian analysis incorporates a lot of hidden assumptions into the numbers, in particular, as you know, the mass function and also the separation distribution. So I think it's actually better, I think surveys should do this, but I think it's actually better to report the results in a more clean fashion, which are just as a function of mass and semi-major axis. Because these numbers are very assumption dependent.
Yeah, I totally agree with you, and I agree that I made several assumptions about the distributions of the planet with mass separations, the eccentricity distribution, the flux, which model did I use. I agree, but I mean, we have to do some assumptions.
Eric?
Well, thank you for the nice talk, Raphael. One question I had, especially following Beth's talk, you looked at almost all the nearby young stars. Did you guys discover any brown dwarfs in the survey?
I think we have 2 or 3 of them, yeah.
Oh, all right, okay. It wasn't that clear.
You published that in the first IDPS paper. I think there are 2 brown dwarfs, no?
Yeah, there's one brown dwarf that was published by David Rodriguez.
Oh, right.
And I believe the other 2 have been obviously published by other people.
All right, okay. So you did find a smattering of young brown dwarfs as well. Yeah, okay.
We have time for more questions. Here?
I can just speak loudly. So you had an cutoff of 200 AU, but certainly at around 15 Jupiter masses, there's a number of sort of 300 AU companions known, quite a number to sort of GKM stars. So the question is, why the 200 AU cutoff? Was that because of biases or?
When we have all these numbers of planets, of candidates to follow up, we had to make a choice. So we said, okay, we will put physical limits in separation between the candidate and the star, and we chose the 200 AU limits. It's
Okay.
just because we cannot have telescope time to follow all the candidates. So that's just a choice.
Okay, so there would be quite a lot more candidates at the 200 to 300 AU
Yeah.
range.
One last question. Sasha?
This is just a follow-up on maybe Laird's comment about brown dwarfs. I think one of the things that we've learned in the last couple of years, maybe from the work of Caitlin Crowder and others, is that if these HR8799 things are common, then we might expect a large number of M-dwarf companions to these A stars. We know that these 8799 things are probably not common. So I'm wondering, it will be interesting to see in the results of this survey what the distribution of binaries looks like, specifically M-dwarf companions to A stars. That's something I'm particularly interested in. And I think along with the snapshot work with Jenny Patience and others at Gemini, it'll be really interesting to see how this story unfolds. The second comment I had was actually just a quick question, and that is, I've been leading a survey at Keck of primarily new stars that were identified by WISE to have debris disks, and we've been actively avoiding the stars that you guys have observed in the last few years, just to avoid redundancy, but we're up to about maybe 170, 180 stars now, and this is being led in the south by Dimitri Mawe. So I guess a quick question is, are all of your stars after 2004 incorporated, do they use ADI type imaging, or is it sort of fuzzy?
I would say that most of them have been, but we should go into the detail to be sure.
Yeah, sure.
Because when the weather is not that bad, so the telescope is open but not that good, so you cannot do a very deep sequence. We still have some data, but maybe there are some of them that we could improve the contrast.
Okay, let's thank Raphael again.